All right, you guys are good to go?
Right. So the use case that I put together for this first demonstration or conversation is using Cloud Composer or Airflow for ingestion of JSON log files into BigQuery. And what's unique about this was, so if you look at what was the key components of this, it was working with a media and podcast advertising merchant. So they were selling advertising space, and at the same time, they wanted to be able to track what ads were sold so that they could tell the advertiser that they had actually targeted the right podcast, and also at the same time be able to identify what spaces had not gotten advertising sold. And so they have a number of logs generated from actual hardware in various podcast providers and those log files get sent up to S3 buckets, and they had made the transition to Google Cloud because they wanted BigQuery analytics. And the challenge was, you can see there on their legacy ingestion process, it was very convoluted. They were using data flow, and they were doing a whole lot of aggregation on data. And so ultimately, in the end, they couldn't actually report out the whole scope of all of the demographic and metadata information that they actually were providing themselves in their log files because of the level of aggregation. And our initial conversation with them was about using Data Studio just for some basic visualization. And in the process, I realized that they were actually losing a whole lot of data, losing access to a whole lot of information and data because of the way that they were processing things. In addition, the data flow, you can't really see it there, but there was Java, there was Python, there was Spark, and so it was a whole lot of different pieces involved as well, and there was no cohesive sense of code to the code base either. And so what I proposed, and one of the things that I thought was kind of silly was that they weren't actually ingesting the JSON file, the JSON logs directly into BigQuery, because BigQuery does a fantastic job with JSON. And in addition, it's a lot simpler. And so if they were actually ingesting the full raw JSON, we could actually, oops, are you still there? I hope I didn't lose you guys. If we ingested the full JSON, they could get the data without the aggregation. So in the end, I've lost the visualize the PowerPoint here, but in the end, the composer aspect was a whole lot cleaner, a whole lot simpler, and one single code base for ingestion of files.
So Chris, so what are the steps? Because I see composer.
Yes.
I think his reception might have given up.
I am here still.
Okay.
Can you hear me now?
Yep.
Yeah. Sorry. Friend, to sell kind of must have failed me there. So, is there any other detail that I can provide on this?
So you had multiple languages. And what technology are you using at the end? Is it all Spark or it's all Python or?
In the end, it's just Python, strictly Python. Because there was no need to actually have any more complex, right? They were doing a whole lot of backflips and rigmarole to create this data set that was aggregated and didn't actually give them the value that log files. Whereas BigQuery does a fantastic job just absorbing a fantastic job just ingest. Yes, I'm still here. Are you there?
Yes.
Hello?
Yes. So
Okay.
you take JSON files.
Yes.
You put them in storage buckets.
Yep.
Then you do some cleaning.
Yes.
And then you put them as is into BigQuery.
Correct. Yes.
Okay.
And the reason we didn't go with data, and the reason we didn't use data flow for this is data flow has no feedback mechanism. So you can use data flow to run Python the same way we did it, but data flow will make it say I was successful or I was not successful loading the data into BigQuery. All it did was initiate a job to BigQuery, and then if the job failed going into BigQuery, there was no feedback loop. So that was one of the reasons we use Composer, because Composer's feed the ingestion into via Composer did allow for that feedback. So if BigQuery had a failure, it would report the failure back and say, we had an issue. And it turned out that was actually a really important piece, because little did we know going into the project, there was no change management on the JSON data structure. And there's one thing that BigQuery does not like with JSON ingestion is changes in the BigQuery structure. So we ended up having to add a little more depth to the actual Composer code in order to either to reject files that weren't that didn't fit the schema.
Okay. So all this complexity in the original processing,
yes,
it's not necessary, or you do it later in the BigQuery.
You do it later, and you do it in the analytics, exactly. So it's more of an ELT instead of an ETL. They were using ETL on it instead of, and so they were losing a lot of visibility and a lot of depth to the data. And BigQuery was a whole lot more fast and nimble in doing, and gave them the ability to decide what their aggregations were. So for example, they added a whole bunch of demographic information about who the target was. Household size, income size, education, all of that was invisible to their original process because it wasn't part of their aggregation layer.
Okay, if you would repeat the same project on a different cloud,
Okay.
Azure, for example.
Right.
Well, Azure has Airflow, so you can do just the same thing, but just change from BigQuery to SQL data warehouse.
Yes. Yep. Exactly.
Will it ingest JSON?
Well, see, so there's the challenge, that right. So with BigQuery, the data is actually ingested in JSON format. So you're querying the raw JSON in BigQuery. So alternatively, if I was to use Databricks, I might actually have Databricks ingest the JSON and then save it to Parquet in a format that was a little bit flatter, or using JSON, or using struct fields, struct field types instead. And then Spark would be pretty nimble. There are some aspects of running queries on massive JSON sets that isn't very convenient. So in some regards, having it in a struct field format might be a bit easier. But the piece that was perfect, what that was really desirable, was the aspect of composed airflow that was desirable was being able to script the particularly identifying the issue. Once we identified the schema change issues that were regular, being able to actually run a schema check on the file and say, no, we're just not going to ingest this file, and then set it aside. And we created a process then to quarantine files that didn't match the schema, instead of trying to build a hammer to beat all of it into submission.
Right. Chris, thank you very much. It was a really great presentation. Thank you.
Yeah, sorry about the transition to the vehicle, but hope it's useful.
Right. So our next presenter is either Rachael or Tyler. Who goes?
I can go if you want.
Okay.
Okay. Do I need to share my screen? Okay. Hold on. Okay. Can you guys see it?
Yes.
And you can hear me okay?
Perfect.
Okay. So I guess, so I think I might have misused the words use cases here, because it's more than I'm actually talking about general architectures. And so I'm going to talk about the Lambda and the Kappa architectures. So I think I have one slide about use cases for both of them because they're very similar. There's a slight difference between the two, but so a Lambda architecture is a data processing architecture that's designed to handle massive amounts of data, but it takes advantage of both batch and stream processing methods. So it attempts to balance latency, throughput, and fault tolerance by using batch processing to provide comprehensive and accurate views of batch data, but also while using real-time stream processing to provide views of more like event type data or online data or anything that's more real-time. It's not quite real-time. I think it's nearly real-time, but yeah, so that's the idea. So it kind of takes advantage of both processing methods. And it was coined by Nathan Mars, which in this presentation, if you go look at it, that's actually a link to, I think his LinkedIn or his website. One of them, the Kappa, the guy who coined the Kappa architecture, I think it goes to his LinkedIn. This one is his website, because he's also the CEO. He founded some company, which I don't really remember all his history, but anyway, but he's very impressive. So, and you can go look at him if you would like to, it's there. So it was created in order to solve the issue of big data needed to be processed, but having too much to process it all in real time, they can't stream everything. So it creates two paths of data flow, a batch layer and a speed layer. So the methodology of the Lambda architecture is there's two layers. The batch layer pre-computes results using distributed processing system that can handle very large quantities of data. That batch layer aims at perfect accuracy by being able to process all available data when generating views. So it means it can fix any errors by recomputing based on the complete data set, then updating the existing views. The speed layer is the data streams or in like real time. And it doesn't have the fix-ups or completeness. This layer sacrifices throughput as it aims to minimize latency by providing real-time views into the most recent data. Essentially, the speed layer is responsible for filling the gap caused by the batch layer's lag. So the batch layer is a lot more stagnant and it takes a lot longer for it to process because it's a batch. And so the streaming process will kind of fill the gap of the time difference between the next time there's more accurate data that's put into like the master data, as they call it. So the speed layer, this layer's views may not be as accurate or complete as the ones eventually produced by the batch layer, but they are available almost immediately after the data is received and can be replaced when the batch layer's views for the same data become available. So they both meet up at the serving layer, which is where the output from the batch and speed layers are stored. And it responds to ad hoc queries by returning pre-computed views or building views from the process data. So I don't know if you guys can see my mouse, but there's the unified log, the event data that comes in. It can go to the hot path or the cold path. The cold path is the batch layer where the master data lives, and then they both meet up at the serving layer. I believe this dotted line is the piece where if something's being recomputed, and then that will go into the serving layer. And then there's the real-time views and the batch views that go into the analytics client. So that's like the end user. That's where they find it. Any questions?
Yeah, actually, this is Chris. So is there the batch view, is that running on a different set of data, or is it running on batches of the stream data that's been captured?
No, so the batch data is stagnant and it stays, it's immutable. You can't change it, but you can add to it. So the gap that the speed layer has is like, so that data is more recent data. It's like the difference in time. So like if you ran the batch, or like the master data was last processed in, the batch layer was last processed like 2 days ago or a day ago, then from a day ago until now, the speed layer kind of takes over, but then eventually you'll get more, when the batch layer runs again, you'll get more updated and accurate data. And I believe that it just kind of, it appends to that master data. And once it's in the master data, it's immutable. Does that answer your question?
I think so. So is the batch data a different set of data that's being aggregated someplace?
Yeah, I believe so.
Or is it okay? Yeah, okay, that makes sense. All right, thanks.
Yeah. Any other questions? And to be honest, Chris, I learned about this myself pretty recently, so I might actually be wrong about that. But from what I read and what I understood, it was in a different, like they were two separate things, and that's why it's probably a little bit harder to manage because of that. But yeah. Okay. So the Kappa architecture is extremely similar to the Lambda, but it is a lot less complex. It's a lot more simple. So Kappa architecture is also a data processing architecture used for processing streaming data, but it does perform batch and real-time processing. But in this case, the main difference between a Lambda and a Kappa is the technology that's used. So in this case, they use a single technology. So Kappa is based on streaming architecture in which an incoming series of data is first stored in a messaging engine like Apache Spark or Kafka. Sorry, I'm so used to saying Apache Spark, like it just came out of my mouth. From there, a stream processing engine will read the data and transform it into an analyzable format and then store it into an analytics database for end users to query. So the Kappa architecture supports near real-time analytics when the data is read and transformed immediately after it is inserted into the messaging engine. So this makes recent data quickly available for end user queries. And it also supports historical analytics by reading the stored streaming data from the messaging engine later in a batch manner. So to create like additional analyzable outputs for more types of analysis. And yeah, like I said, the main difference between them is that the Kappa architecture is all data is treated as if it were a stream, and the streaming process engine only uses one data transformation engine. So the difference with that one, it looks kind of similar in the sense like it has the event data, and then it has the speed layers that real time, and then you've got the long-term store, which is master data. But in this case, you have recompute log events from storage if you need them, and they go into that speed layer, and then you have the analytics client in the end. So it's just like a simplified version of the Lambda architecture. So the data is ingested as a stream of events into a distributed and fault-tolerant unified log. These events are ordered, and the current state of an event is changed only by a new event being appended. And then so if you need to recompute the entire data set, equivalent to what the batch layer does in Lambda, you simply replay the stream, and typically using parallelism to complete the computation in a timely fashion. So any questions about that?
Not necessarily a question, but a comment. The replay of messaging logs via something like Kafka is becoming more and more a storage engine type and data processing type of system. So that's interesting. I didn't know it was actually had a name, but we've actually looked at this on the Greenbrier project a bit.
Oh, okay. Yeah, that's cool.
I have a question. If for long-term storage, we're using a data warehouse and we have, let's say, terabytes of data. So if we're switching to Kappa architecture, does it mean that we now keep terabytes of data in Kafka, in speed layer, in messaging?
That's a good question. I would
Yeah, that's
imagine-
actually the intention.
Is it? Okay.
Yeah, and that the idea is that the log becomes completely immutable then, and you can go back to any point in time and to run your analysis. You can say, show me what it looked like 3 weeks ago, and you can do that.
Well, that's cool.
So now you're saying
Yeah.
Kafka is a new data warehouse.
That's what Confluent would like you to think.
Well, cool. Thanks for giving that little piece of info, Chris.
Yeah. I gotta hop out now, but thanks. Good to hear your voice, Rachel, and
Yeah,
everybody
you too.
have a good night.
Have a good night,
Thank
Chris.
you. Thank you, Chris.
Happy holidays. Okay, so I did put a few use cases in here. So these are actually specific use cases that are being used today, or at least when I read the use cases that I was reading, but Meta Markets, which provides analytics for companies in the programmatic advertising space. They employ a version of the Lambda architecture that uses Druid for storing and serving both the streamed and batch processed data. So I have a link on these ones too. So if you want to learn more, because I don't actually know anything about Druid. But this is what I found out on use cases, like specific ones. So for running analytics on its advertising data warehouse, Yahoo has taken a similar approach, also using Apache Storm, Hadoop, and Druid. So there's a couple use cases there. Of course, both of these use cases use Lambda, but Chris was talking, and it sounds like he has actual use cases for the Kappa architecture, but they just didn't call it that. So that's kind of, might have to ask him more about that. And then that's it. Were there any questions other than the ones you guys asked?
No, it was very, very interesting. Thank you.
Yeah. yeah, it was interesting for me too, because I didn't know a lot of that. I didn't know a lot of that stuff when I was starting to look up the architecture stuff and started seeing all these different ones. They had a few more in the article I was reading, other, specific architecture types, but those were the two I decided to share with you.
Rachel, and I also want to remind that it was your idea to actually include use cases in the seminar, and now we have second session, and it's really, really interesting and really, really useful. So I want to thank you for that.
Oh, yeah. I definitely think it's like nice. It puts it in perspective of like, why would you use this? Where would you use this? What would be the benefit of using this one over another one and stuff like that. So I definitely think it's good for all of us to know.
So now we're switching to Tyler. Tyler, can you show your screen?
Yes. Okay, is everyone able to see it?
Yep.
Okay. Yeah, so let's see what I'm going to be covering for my use case. It was a scenario that came up with a client I worked with. So rather than discussing a particular loading pattern, which I think a lot of good examples there have already been covered, but I'm going to switch a little bit to covering data security. So yeah, with this particular client, they were very focused on determining how to come up with an overall security architecture for their solution. So they, while they were interested in building out the solution for loading data, the security was definitely a big piece of it. So in trying to develop a strategy for them, we followed this path, and I'll walk you through that. So one of the things to look at while trying to design a strategy for data security, you can consider three questions as you follow the flow of data from its source through transformations to its final consumption. So things you can think about along the way is, who owns the data? So at each step along the way, who's really responsible for, generating it and maintaining it? Then who manipulates the data? So who on the team is responsible for transforming that data and getting it cleaned and mastered and whatnot? And then finally, who can access the data? So, at the various points along the way, who's able to read it and potentially interact with it. So specifically with accessing the data, we also are interested in subsets there. So one is what's the group of people who have full access to all the data versus which groups of people may only get access to particular subsets of the data. So these are all questions that can help develop the strategy for data security. So one of the things you always want to focus on is the principle of least privilege. And that's the idea that users who are accessing the data in your system should be given the fewest possible permissions required to allow them to do their jobs, and then make sure that they don't have anything beyond that. So some examples of where you may want to use least privilege is, for developers in your environment, they'll need permissions to be able to manipulate the data, but they don't need admin permissions, for instance, particularly not in a production environment. Maybe you might be a little more lax in a development environment, but in production, certainly they shouldn't need admin permissions. Likewise, analysts who are viewing the data and doing some number crunching, they shouldn't necessarily need write permissions on the tables that they're accessing. They, in most cases, read only should be sufficient. And then another potential scenario would be deployment managers. So as code is being written and pushed from one environment to the next, they need permissions to be able to deploy and write out the various structures but don't necessarily need permissions to be able to read the data itself. So these are just some examples of the principle of least privilege. So moving on, just to give a little idea here, as we discuss further a potential strategy. And for some reason, this Visio diagram isn't showing up quite right. Not getting a lot of the text in here, but overall, just for this simple reporting architecture, over on the left side here, left of the dotted line, these are representing external data sources. They're coming in, and then this is an orchestration. So Azure Data Factory or Synapse pipelines or whatnot. This example focuses primarily on the Azure Azure services that are available. So yeah, again, this diagram did have text in here explaining what all this is, but I'll just talk through it. So this is the orchestration piece within Azure Synapse. This overall box is Synapse. And then you have your SQL database within the Synapse. And then you have, you can build reporting views in your database to surface the data to people building reports. So you can have it in Excel, Power BI, other reporting tools. And then also the orchestration will push data out to a data lake, where again, this data and more, the file formats could be accessed by reporting tools. So an alternate method of being able to access that data. And then I have another piece here that's using a logic app to send email notifications to users. So with that diagram in mind, it's helpful to think about then the various data touch points along that data journey. And so different users will need different access and different levels of permission to the data at various points along that journey. And so some of those touch points that we want to look at, again, referencing that prior diagram, we have the source data systems, the orchestration systems, the raw storage and data lake, the transformed and cleaned data in the database, and then data that's surfaced through the reporting layer and visualizations. So now to further help with the design and the strategy for data security, you want to leverage security roles. So again, talking about Azure and the Azure environment, you'll most likely be working with users who have users configured within Azure Active Directory. So rather than granting permissions to individual users, you definitely want to use security groups within Azure Active Directory, and then assign those security groups to the different security roles. And so we discussed in the previous slide the various touch points, and then for each of those touch points, you'll want to consider what types of roles you want to have for users who will be interacting with that data. And so at each of these touch points, you'll generally want to consider at a minimum 3 different levels of security. So one would be the administrators and owners. So these are the people who have full unfettered access to the data and resources at that particular touch point. Oh, sorry. And then and they also have the ability to manage other users as well in that environment. Next one is your power users and or developers. These are users that have a little bit more restricted access, but still have, generally a lot of leeway for reading, writing, and modifying data. And then finally, you've got what would be considered your standard users, who really are just consumers of the data. And so they'll generally just have read only. And in some cases, depending on your environment and what you're needing to do, they might have write permissions, but yeah, generally we'll assume that they only need read permissions there. So now to further help organize all of these different roles in the various touch points, we can use a data security matrix to help us define how the security should be laid out. So here we have an example that shows in these the gray bars here different touch points along the way, like we discussed in a previous slide. And then underneath that, we have different built-in roles that are defined. And then along the top, we have our security group roles that we've defined. And so we're using the matrix to say, you know, at each of these points, which of these security groups should be assigned to which of these roles. So just in this example here, these are some of the built-in roles for the role-based access control in Azure. So you have your Synapse administrator, which has full access to the Synapse workspace, and you can see we have a security group set up that's the Synapse admins. And so that Azure security group would be assigned to this role in that resource. Then your ETL developers, again, you know, in this case, we're saying that they would have a couple different roles that they could be assigned to within Synapse, but then also they would have certain permissions in other resources as well. And then you can go continue through with each of your security groups that you've set up. And then another level of helping to organize is not just at the resource level, who has what access and what permissions, but also at the specific data level itself. So here we have a matrix for any given data access persona. So again, these could be roughly analogous to the security groups that you have set up, what levels of access they would have to different data. So if we say here, you know, for a manufacturing company, that say we have different areas of data within the database. You know, we've got some data about our materials, data about plants, inventory levels, and so forth here. Then you can decide for each of these roles, should any of these roles have full access to that data, limited access to that data, or no access. So an example here for, say, limited access, you see this enterprise data analyst has limited access to the material information and plant information and inventory levels. So in that case, you could say, well, you know, what we're looking at here is we're assuming there are different departments. So this data analyst, they might work, or you say they work in a different plant. You know, they could get information related to materials and inventory within the specific plant where they work, but they wouldn't have access to data in the other plants. So that's why it shows up as limited here. And then some users wouldn't need any access at all to that. So you can use a matrix like this to further help organize and determine your security strategy. And then finally, once you have everything planned out using those matrices, then you can go ahead and go into your resources and your databases and start actually assigning those roles as you've determined. So yeah, that pretty much sums up my presentation then on data security. So are there any questions?
On the previous slide, you had a row where it says no for everything. Oh, no, I'm sorry, not everything. I see the accessing. Okay, sorry.
Okay. Yeah, probably for these HR roles.
Right.
Yeah, so for these ones, I was kind of illustrating that we might have just some HR data in the database. And so they wouldn't necessarily need access to more of the operational data, and they just instead get access to the HR data.
Mm-hmm. But you said
Now-
that roles are set in the Active Directory. But what about access for particular tables, for particular rows and columns? This should be in the data warehouse, right?
Right. Yeah. So there, yeah, a lot of different levels of data. So these here really help organize two of the big layers of access. So this is at a very high level at the resource level. So determining who has just any kind of access to the database or you know, the SQL pool or the data lake, and determining where people should have the permissions to be able to access the data. And then once you determine which services can be used for accessing the data for different users, then this persona matrix helps drill down a little further. And so for these individual data domains, that would help determine how to assign permissions to individual schemas within the database or individual tables. And then particularly in the case of the of these limited access rows here, you might want to even go down to row level security and apply rules there that would limit the specific rows that a user can view.
All right. Thank you.
Yeah, you're
So
welcome.
if you're doing continuous integration, continuous delivery, do you keep these kind of things stored in some of your files repositories there?
Yeah, so within the database itself, typically you'd have code that would be written to specify who has the permissions to what. And so that could be deployed in your CI/CD pipelines as well. Let's see. You could presumably do it programmatically too at the higher level for the resources themselves. So yeah, you could parameterize that and manage it programmatically through CI/CD pipelines at this level as well.
That's useful to do it that way, or is that just kind of overwork?
Personally, I have not done that. Just since with the changes that you would deploy from one environment to the next, you know, particularly if you just have 3 environments that you're setting up, you know, like a dev, test, and production. Generally, when you're first spinning up your resources, then you would assign those permissions. So if you have a limited number of resources, it's probably just quicker and easier to assign permissions manually.
Right.
But if you had a type of scenario where, you know, you have dozens or hundreds of different SQL pools that you're trying to spin up in each environment, then you'd want to figure out a way to do that programmatically and then take that approach.
Yeah.
Yeah, people definitely do it programmatically in big organizations with thousands of people. So they have scripts which assign specific roles and permissions to people.
Right.
Okay, we're probably out of time, right? Tyler, it was very good. Thank you.
Thank you.
Thank you.
And by the way,
Yeah,
the
thank you,
things
Tyler.
Thanks.
which were not seen is because you opened it in the browser. If you open PowerPoint on your desktop, like everything looks fine.
Yeah, I should have done that instead. Yeah, apologies for that.
Okay. Well, happy holidays. We will not meet this year.
Yeah.
See you next year.
All right, see you guys.
Thank you.
Thank you.
Yeah.
Happy
you very
Great
holidays.
much.
holiday, everyone.
Thank you very
Happy
much.
holidays. Thanks, guys.
Yeah.
Thank you. Enjoy. Yeah.
Bye.
Okay. Thank you, Taylor. Thank you. Bye.
Thanks. Bye.
Yeah. Bye.